OpenAI managed to use one of their models to disprove what they call a central conjecture in discrete geometry. Specifically, it's the unit distance conjecture posed by Erdős about 80 years ago. And most of the coverage of this news doesn't tell you that much more than what I just said in 3 sentences. We want to cover this topic and the problem in more depth, and also talk about what this news and AI math in general means for the future of mathematics, or more provocatively, will we have mathematicians in 2030? We had a call about this with Vašek Rozhoň, one of the Polylog members that you don't usually see on camera, and for the most part it will be him talking because he knows a lot about this kind of math and he knows a lot about AI math. So without further ado, here's the disproven unit distance conjecture.
So I think that many of our viewers know the name of Paul Erdős. He was this amazingly prolific mathematician in 20th century, doing mostly combinatorics and discrete mathematics. He was just solving problems left and right, and he was making conjectures left and right. He actually sometimes offered money in the sense that he said, like, look, if you prove or disprove my conjecture, I will give you some money. Oftentimes it was maybe like $1,000 or something like that. Literally the hardest way of earning $1,000 is try to prove or disprove a conjecture by Erdős, because he was amazingly good. Yeah, going back to his problem, the statement is actually incredibly simple, but like once you start thinking about it, it's like really hard, right? Put endpoints in a plane to maximize the number of pairs that are the same unit distance apart. So this picture that I'm showing, it shows something like 10 points in a plane, and I have put an edge between a pair of points if they are distance exactly 1 apart. So you can imagine that I take a ruler and I kind of look at all of those pairs, all of them are distance 1 apart. The question is very simple. If I give you some number n, you should put n points on a plane so that you maximize the number of such pairs. It's really not a question about n equals to 10. It's a question about what happens when n grows to infinity. It's a very simple question, but it's very hard to answer. People realize that it goes actually quite deep. So one construction could be square grid. You can say for any n, put root n times root n points in a grid, and that's it. That will generate maybe many unit distance pairs. In this example, everybody has 4 bodies, right? North, west, east, and south. So the number of unit distances that you generated is something like 2m. That's actually not very much, right? On the other hand, you could hope that maybe there is some kind of absolutely insane construction where there could be as many as n squarish pairs of points. So this is what Erdős is asking about. He's asking this asymptotic question. So Erdős himself actually tried to answer this question, and he concluded that, probably it's impossible to have a dense point set. He thought like, probably it's impossible for there to be a point set where you would have like n to the 1.00001 many edges. And he had 2 reasons for it. The first one is so-called upper bound. He kind of proves that for any point set, there can be at most n to the 1.5 many edges. So let me explain what this upper bound is and like why it gives us some intuition. Erdős's absolutely amazing and genius idea is to count cherries. Okay, so what is a cherry? So cherry is this configuration. You take 3 points, such that 2 of them and 2 of them are unit distance apart. And he says that, look, on one hand, in any point set, there cannot be too many cherries. So why is that? Well, think about picking any pair of points, okay? How many cherries can these 2 points define? Well, actually just 2, right? So there's like this cherry and that cherry, but there are no other cherries possible, which means that the total number of cherries is like relatively small. It is at most something like 2 times n squared. So, okay, on one hand, the number of cherries is small. On the other hand, he realized that if there were actually many edges in my configuration, if there were many pairs that are unit distance apart, that would actually mean that there would have to be super many cherries. So why is that? Well, there is another way of how we can count the number of cherries. We can just say, pick any point and think about it as a center of a cherry. If you have a point and it has like, 100 edges around it, the guy has like, 100 bodies of distance 1. How many cherries does this guy define? Well, it will be something like 100 squared, right? Because for any pair of bodies, you can kind of connect them in a cherry. In reality, it would be some kind of binomial coefficient, but asymptotically, that binomial coefficient is roughly the number of your bodies squared. So now you can start running algebra autopilot, sum up this thing over all of the vertices in a graph. You can use something called Cauchy-Schwarz inequality. And long story short, you will get another bound for number of cherries. And that's great. You can kind of put these 2 bounds together. And again, after some algebra autopilot, we find out that the number of edges has to be at most like n to the 1.5. Okay, so we were counting cherries, but maybe if we were counting something more complicated, or if we had like more advanced argument, we could probably push this further, right? Maybe we could go from n to the 1.5 to n to the 1.4, 1.3, and so on. Ultimately, it's like very plausible that if we do some version of this argument on steroids, we would get all the way up to proving that n to the 1.0001 is impossible. This is one intuition why kind of Erdős believed that the right answer is probably n-ish. He also had a second intuition, that was that he actually tried to come up with some point set that would have n to the 1.000001 many edges. He almost got there, but not quite, he failed. And this is why he conjectured that, look, it's probably not possible, right? His point set was actually just a grid. Erdős had like the following idea. He said, look, maybe instead of looking at distance 1, we can look at distance maybe 5. So let's see how many bodies everybody has at the distance 5. So let's pick the center vertex and let's look at the bodies. And actually now there are many more of them. And why is that? Well, 3 squared plus 4 squared equals 5 squared. It's like this thing that you may learned in high school, Pythagorean triples. So you are doing better if you are looking at distance 5 than if you are looking at distance 1. I defined the problem as a unit distance problem, but actually, if you just scale this whole picture by 5, then they will be unit distance apart. So we don't have to talk about unit distance. We just have to pick some numbers, some distance, and then count how many pairs are there of that distance. So let's look at 65 actually. Everybody has just so many bodies, right? It's actually insane. The question is like, why 65? What's so interesting about 65? And this is what Erdős worked out, a general formula that lets you compute the right distances to look at so that everybody has extremely large number of bodies. So here is how you can construct these numbers. I will not prove it because I would need some kind of number theory for that. You have to look at prime numbers that have remainder 1, floor 4, okay, for whatever reason. So for example, 5 divided by 4, the remainder is 1, right? And 13 divided by 4, like the remainder is 1, and so on. And what Erdős worked out is that if you just keep multiplying these prime numbers, then you keep generating the right distances. And then he kind of optimized this construction for general n, and he found out that he could create a point set, which would be just like a grid, that generates something like n to the 1 plus 1 over log n many edges. This is like some really weird, complicated function, but like, although this function kind of grows faster than n, it still grows smaller than n to the 1.1 or n to the 1.0001. Any number larger than 1 that you put in the exponent, this function grows slower. Okay, so even Erdős failed to construct an example, so probably there is no example. Now, the big breakthrough by GPT is that it didn't fail. GPT managed to construct a point set with something like n to the 1.01 edges per endpoint. This problem is still very far from being solved. But the thing that we now do know is that Erdős was wrong. Whatever the answer is, and it will probably be very hard to find it, we know that it is somewhere between n to the 1.01 and n to the 1.3. I would like to tell you a little bit more about how the construction by GPT works. It's actually hard. So first of all, it's hard for me. It's kind of a little bit beyond my pay grade, to be honest. And even if it wasn't, it would be actually quite hard to explain it quickly in this video. This is the best picture that I got when I was trying to recreate the construction of GPT. The construction is very asymptotic. It kicks in only for extremely large values of n, so it's quite hard to make it work for small n. It's also kind of underdefined, so it's not like there would be one single picture that would work. There are like several instantiations of how to make the construction by GPT work. So let me just say one thing about it. What GPT is doing is that it basically follows Erdős's footsteps. GPT kind of takes his general approach, generalizes, and then it uses a bigger hammer than what Erdős was doing. Erdős already used some number theory, but it was the kind of stuff that people knew in the 19th century, let's say. What the GPT is doing is more complicated. It uses some more heavy tools from this area called algebraic number theory, and somehow it makes it work. The thing that I would like to comment on this is a more general observation about the nature of the solution. So the solution itself is actually relatively straightforward. So OpenAI's paper has maybe something like 20 pages, but like the math in it, you could probably compress it into 3 or 4 pages. So the solution itself is relatively straightforward, but the hard part, in my opinion, is kind of to understand algebraic number theory well enough. This goes back to what are the main strengths of LLM currently, and what are their main weaknesses. The main strengths of LLMs, as I see it, are, well, memory. Already GPT-3 could speak like, I don't know, 30, 50 languages. So it had amazing memory. And GPT-5, it actually understands pretty much the whole mathematics across all the subdomains. So if you have some kind of problem that you can solve by taking what is known in discrete geometry, the sub-area where this problem is coming from, and if you can combine it with your knowledge of algebraic number theory, human mathematicians, well, there are not so many people around that would actually both understand discrete geometry very well, and that would also understand algebraic number theory deeply enough. But LLMs, they do understand everything very well. Okay, so this is their main strength. And on the other hand, like the current weaknesses of LLMs is that we still do not have great ways of how to turn compute during test time into results. What I want to say is that if you give me a lot of time, I scale better than LLMs. The extreme example of this would be Andrew Wiles, who solved last Fermat theorem, and he needed like 7 years to that. If you give me half a year and let me work on a problem, I will probably get further than if you give half a year to GPT-5. GPT-5 will probably relatively quickly start going in circles. It will not know how to proceed. Of course, this will absolutely change in like half a year or a year. So I can actually start by telling you some results of my experiments, right, that I did with our system. Even with our like very limited setup and very limited money that we are throwing at it, we are actually able to basically produce like a few diploma theses or like few undergrad theses per day.
Yeah.
Sure. These are not some spectacular results because we are not having like, the state-of-the-art models, but also like most of the problems that mathematicians think about are kind of much easier than Erdős problems. I'm thinking about like this sea level, which is rising. Sea level is currently like around undergrad thesis or like diploma thesis. And this waterline is something very different than what is currently the best produced result, this Erdős unit distance problem. This is like way better than what most mathematicians, including me, produced ever during their lifetime. I still hope that I'm currently a better mathematician than waterline. But my point is that the waterline will steadily rise until it will reach the height of solving this unit distance conjecture.
There's this quote that I heard, like average mathematicians write proofs, good mathematicians write conjectures, and the best mathematicians write definitions. And so it's harder for me to see that being automated, or like perhaps the fundamentally human part of mathematics is like deciding what are even the things that we consider interesting in the first place, because there's so many mathematical statements that we could prove, and only some of them do we consider interesting or elegant.
No, I think I completely agree with you. In some sense, asking the right question is just the hardest part of mathematics. And so this will be kind of the last stand of humanity. Whether you asked or not asked the right question, you will learn only in maybe 10 years of time, right? So it's like extremely difficult problem to evaluate. But I don't see any like qualitative reason why it shouldn't happen. It will be just another data point on this exponential.
But then what is the verifiable reward, right? Like if I'm like Claude Shannon and I'm starting information theory, like what is telling me that I've made the right move and I've made the right definitions and that this is something that's like useful and interesting to think about?
Typically in mathematics, you will learn it by seeing applications at some point. You can be like Grothendieck, who was proving some incredibly abstract theories, but right now when people are looking back, they are actually showing relatively concrete applications of it, right? There are some mechanical aspects of checking whether your big idea was right or not. I totally agree with you that this is really hard, and beauty plays also part in this. But again, beauty is something that in some sense is a little bit mechanical, right? Because
that's a hot take. That's a crazy take.
Look, Kolmogorov of complexity, right? Beauty is in simplicity.
Yeah.
Like
now we're talking in the strictly like beautiful mathematical statements, right?
Yeah, exactly. I'm not talking about like beauty of flower. I'm just talking about like, when mathematicians are like claiming that theorems are beautiful. What I'm saying is that this is not magic. There are some mechanical components to it. But first of all, I want to say that like, maybe AIs are actually already beating us in this aspect of mathematics right now. Most mathematicians never get famous for asking a question that started a new field or something like that. Right?
Yeah.
Mathematicians are much more like, down to earth. Prove the question that your colleague asked 5 years ago or something like that. Right?
Yeah.
So they are saying like, look, in some distant future, like, in 3 years, AI will get better than us. But actually, maybe it already got better like 3 months ago. It's hard to say, right?
It's hard to say, yeah. Okay, so thanks for watching. This has been our exploration of OpenAI's new result. We hope you enjoyed the new format. Let us know. We're sort of always happy to experiment with new things. And obviously, because this is time sensitive, the format is a bit different. Less animations. We're talking off the cuff and it's not a prepared script. Let us know what you think about it. Should we do more of this? Should we never do this again? Let's see what happens.
Okay, bye.
Bye-bye.